Hello, everyone. Thank you for being here today. I know it's been a long day, and there were many interesting talks in the time slot, so I really appreciate you being here. Hope you've been enjoying your time at KubeCon. My name is Erikson, and I work on the Compute Runtime team at Netflix. And today I'll be talking to you about container runtime customizations at Netflix. In terms of the gist, I'll be sharing how we use runtime extensions, such as the node resource interface plugins and OCI hooks to handle some of the unique platform requirements of Netflix's compute platform, Titus. Okay, so here's the agenda of what I'll be going over today. I'll start off by describing the problem we faced around the same time last year, or around this time, where we were trying to migrate years of accumulated custom runtime code to a more standard Kubernetes dataplane implementation, consisting of standard tooling like stock, kubelets, and containerd. Then I'll kind of share some our guiding principles, philosophies, and strategies for kind of migrating user workloads to this new modern stack and how that kind of influenced our implementation. Next, I'll kind of go into detail of the runtime extensions we leveraged, chiefly the NRI plugins and OCI hooks. Then I'll give some concrete use case examples. Think for things such as CPU isolation, trying to run systemd in a container, and trying to control the workload lifecycle. Then I'll share some experience of us running these runtime extensions at scale in production and some of the challenges we faced. And lastly, I hope to share some key learnings and takeaways from our modernization projects. And hopefully by the end of the talk, I'll have some time for questions. By the end of this talk, I hope you'll walk away with ideas on how to handle your own unique platform requirements using these runtime extensions. There's no need for Kubernetes or rewrite your workloads. There are tools available for you to achieve what you need to do. So let me start off with some context. You might have seen this slide in some of our previous presentations from Netflix. So what is Titus? Titus is Netflix's container platform. It's been running production workloads for almost nearly a decade. Originally, it was conceived in the early days of cloud native, before Kubernetes was becoming more mainstream. Originally built on Apache Mesos, and when Kubernetes became more dominant, we swapped out the underlying control plane with Kubernetes. But critically, during that time, we decided to leave the dataplane implementation intact. This becomes a rather important detail, which I'll kind of delve into later. So today, on Titus, we run hundreds of thousands of pods globally at any given time. It powers both our streaming and non-streaming applications in Netflix. It hosts a very diverse set of workloads. So we run batch jobs for encoding. We also have data pipeline jobs. And more recently, more relevant today, we have a lot of machine learning workloads that powers our recommendation systems. So what was the problem we were trying to solve? When we adopted Kubernetes control plane back in 2018, when we did that migration, we still had a lot of unique platform requirements coming from our users, and we had to implement that in our data plane that just did not lend well to the Kubernetes model. We have developed our own patterns and methodologies for orchestrating containers with multi-tenancy features before Kubernetes best practices and cloud-native conventions have solidified. And to migrate our data plane implementation back then, we used a tool called Virtual Kubelet. Virtual Kubelet is this open source framework that essentially lets you masquerade as a kubelet to the control plane, but you can dispatch container execution to a custom backend. This was the mechanism that allowed us to preserve our existing runtime implementation at the time. So the custom runtime layer was called Titus Executor. It's this very monolithic runtime layer. You can think of it as the CRI implementations of today that essentially did everything to set up a Titus container to run it through Docker. And this was also before Docker Shim was a thing. And this particular piece of software had grown rather unwieldy as we kind of piled on more business logic, more platform requirements over the years. And this custom stack had been increasingly becoming hard to maintain. The way we were using Docker as an underlying container runtime for running Titus job had also proven to be somewhat brittle and not very scalable. And by tying our runtime to Docker, we couldn't adopt standard case tooling and new innovations in the container runtime space. And most critically, with Docker long deprecated in Kubernetes, we just really needed to modernize and get with the times. Which then leads to our goal. Our goal was to migrate to a more modern runtime stack. And what does that mean? We wanted to align on industry standard tooling versus relying on these bespoke, homegrown container runtime components. And what that really meant was adopting stock kubelets and Containerd as the main runtime components in our data plane. And by adopting real kubelets, what we were able to shed was all this undifferentiated work we did around pod lifecycle management and all the interfacing with the control plane that we had custom code around. And by swapping out Docker from Containerd, this opened a door for us to many new innovations like different snapshotters that we can try out for improving image pull times and unpack times. But this goal doesn't come without its own challenges. The big challenge here was that we had years of custom runtime logic to preserve. Many of Netflix's workload come from the EC2 era, where they expected VM-like environments. So you have systemd running as a init, as a service manager, and users on our platform also expect platform services to be running under systemd in the same container namespace. We also had multi-tenancy requirements, such as user namespace isolation, which fortunately has been supported in Kubernetes recently in 1.33. Another thing was CPU isolation and workload tiering. Another core goal of the project was that we mustn't disrupt our existing user workloads. Maintaining trust in Titus as a compute platform was paramount for us. And the reality of the situation is we built Titus really early, before cloud native has so truly solidified. We adopted containers early and developed our own methodologies that made sense at the time. And our users have built their software and deployments and additional abstractions on top of these patterns. So the key question became, how are we able to preserve all this behavior while modernizing our runtime stack transparently to our users? Our migration philosophy essentially came down to balancing two goals that are our intention. On one hand, we wanted to align with industry standards. As mentioned earlier, we want to adopt real kubelets, Containerd, use standard Kubernetes primitives wherever possible, and identify anti-patterns and remove them to our best of our ability. But on the other hand, we also had the mandate of essentially trying to keep zero user disruption during this whole process. We want to ensure a transparent migration where existing workloads just continue walking on Titus. It will just keep working even after we swap out the engines. So in the end, the strategy that we settled on was, let's just take the biggest step we can towards industry alignment without breaking our users. Let us build a solid foundation on standard runtime components first, then we can iteratively move towards the more modern, more conventional methodologies. Okay, wait, oh, there we go. So tactically, how do we apply this strategy? Rather than rewrite everything from scratch, we took a lift and shift approach. We broke up our existing custom runtime code and relocated each piece of functionality to the appropriate runtime extension point. This approach has three key benefits. First, we minimize risk by reusing the same battle-tested code that we've been running in production for years, and we have extensive integration tests for. Secondly, it allowed us to easily validate the new runtime architecture with real workloads without forcing major change on our users to change however they deploy or however they package their software. And third, most critically, we can reduce operational complexity. Because we have a transparent migration, we could switch user workloads over quickly and avoid having to maintain two different runtime stacks in parallel for too long. And here, I have an excerpt from an excellent blog post by one of our fellow engineers on the compute runtime team, Kyle, that talks about how to migrate complex systems and infrastructure. And it reads, minimize the time you Roman ride at all cost. Do not underestimate the burden of Roman riding. Roman riding is the practice of trying to balance on two horses that are galloping forward at full speed. In the context of platform engineering, we are the person balancing on two horses, and the horses are our two different systems that try to accomplish the same functionality. And the burden of operating those two systems, it doesn't just grow linearly. It's more of like a 4x increase because of all the inter-system interactions and all the context switching you have to do when you're operating into two systems. So moving on, that's enough of context. I'd like to talk about the actual extensions we use for our modernization projects. One of the first things that cluster administrators consider when they need customizations at the pod level is usually admission webhooks. They're widely used for policy enforcement, injecting sidecars, injecting environment variables and volume mounts. Many platforms rely heavily on webhooks, but webhooks have a fundamental limitation here. They run at the K8s API level before the pods actually get scheduled onto a node, and they can only mutate the declarative pod spec. For us working on Titus, we need to do things like inject processes into existing container namespaces at runtime. We also need to dynamically determine and force CPU isolation, and also control workload startup timing. You simply cannot express these runtime operations in a pod spec. We have to manipulate the container after it has been scheduled onto a node. And this is where runtime level extensions, like the node resource interface plugins and OCI hooks, come into play. So the two key runtime extensions we leverage are the node resource interface plugins and OCI hooks. NRI plugins are these long-running processes that register themselves with the OCI-supported container runtime, like containerd. They can modify the OCI runtime spec before the containers get created, and they also can perform additional actions at specific pod and container lifecycle events. And these events usually map to different CRI requests for creating and deleting containers and pods. And because they're always running on the node, they're great for coordinating runtime operations that need to span multiple lifecycle events. And they're also great for making no-level runtime decisions. OCI hooks, on the other hand, are short-lived executables invoked at different container lifecycle moments, like pre-start, post-start, and post-stop, which are defined in the OCI runtime spec. These hooks, defined by the OCI runtime specification, depending on which hook, the operations can happen directly in the container's namespace, which we do use for things like creating Sentinel files, directories, sockets on our users' behalf. Another neat property of OCI hooks is that they're guaranteed to execute by the lower level runtime, like runC, as long as configured in the OCI runtime spec for each container. This makes them particularly reliable for critical operations like cleanup and teardown. Even though other components fail, and a container is running, the hooks will still run as long as they're declared as part of the runtime spec. Next, I'll show how these extensions fit into our new runtime stack. So here we have a table that shows the different runtime extensions that we leverage as part of our modernization efforts. So we do still use admission webhooks. We do use admission webhooks for policy enforcement. So for example, if a pod comes in with a ridiculous request for memory or CPU, we outright just reject it and not let it just sit in pending forever. We also do pod spec mutation to add pod annotations that eventually drive runtime behavior. Next, we also have our own CNI plugin. We use it for IP assignment, container networking, to adapt to some rather special requirements of Titus's container networking story. And we have a talk back in 2014 in reInvent that kind of goes in detail if you're ever interested of how we kind of do IP address assignments. So I recommend that talk. Next, we have NRI plugins, as mentioned before. We use it we do use it for OCI runtime spec modification, and we also use it for coordinating the startup sequence of our Titus workloads. Next, we have OCI hooks. As mentioned before, we rely on them heavily for cleanup whenever containers stop, and we also do direct container modifications when the containers actually are created. Lastly, we have this little piece of software called the runC wrapper, which fills in any last-mile OCI spec adjustments that NRI doesn't currently support in terms of adjusting the OCI runtime spec. And this particular piece is something that we don't intend to kind of maintain long-term. It's more of like a place where for things like SecCom policy, for example, that wasn't recently supported in the NRI adjustment API, we had to kind of do it in the runC wrapper. But as as NRI support more adjustments, we'll eventually get rid of this layer. Next, I'll walk through some concrete examples of how these extension points work in practice. So for example, we have systemd supports. As I touched upon earlier, a lot of Netflix workloads expect systemd to be present, supervising their workload processes in the container. Users also expect this familiar debugging setup whenever they get a shell into their workload runtime environment. So things like systemctl and generalctl, our users are very familiar with using these tools for debugging their workloads. They also expect services providing platform functionality to be in the same container. So in the end, what do we have is a multi-process container with systemd doing init and service management, and this is all decidedly anti-pattern. But in the interest of our users enabling transparent and painless migration to a more modern stack, we needed to support this use case. In order to run systemd in a container, it needs specific mounts configured at the OCI runtime spec level. An example is systemd that expects dominion over its own cgroup FS. So we mount one in the main applications container. If you can just note the code over here, you can see the type here is actually cgroup. This type of low-level mount configuration is simply not available in the pod spec. So this is an example of a straightforward OCI runtime spec modification use case, demonstrating how NRI can be used to support unique workload requirements. Next, we have CPU isolation. The CPU isolation example here demonstrates no-level runtime decision. In terms of flow, how it works is that the Titus control plane sets a CPU tier via pod annotations, dictating whether the particular workload should use exclusive CPU or shared CPU pools. The NRI plugin then removes the kubelet's default CPU settings and delegates to a no local service that we call Titus isolate. Titus isolate is responsible for tracking CPU allocations. For the exclusive tier, it assigns dedicated CPUs via CPU sets. For the shared tier, it assigns quota in a shared pool depending on the workload priority. This differs from the Kubernetes CPU manager, which only works for pods with guaranteed QoS settings and static policies. Our approach supports multiple workload tiers and decisions at the container creation time based on what's currently available on a node. We cannot determine this at pod admission time. NRI instead is able to call out to a no local service with full visibility into its current CPU allocations and the topology of the actual node. Next, I'd like to share how we run these platform functionality services. How we run them today is also an anti-pattern we're lifting and shifting. We run per pod platform services as systemd service instances on the host. For things like an instance metadata proxy, service secret management, metrics, and logging, we have individual platform service instances for each of those. The NRI plugin is responsible for managing the lifecycle of these platform services. It handles setting up volume containers for pulling down these actual binaries and starts the actual systemd service instances. And these service instances exec directly in the container's namespace. After we confirm that the platform service has fully started, then NRI is also responsible for telling the workload in the container that they're actually able to run. In terms of the shutdown path, we leverage OCI hooks. OCI hooks is responsible for stopping the systemd service instances when the pod actually terminates. In the long term, we want to move these to sidecar containers, which is more aligned with the cloud-native approach. But extension points lets us preserve the existing pattern during migration while we build the foundation for our new modern stack in a transparent manner for our platform users. We can evolve towards sidecars incrementally. Now, let me show you how all these pieces come together. So here are two diagrams showing the application lifecycle orchestration. We orchestrate both at the pod startup and tear down levels through extension points. For startup, we inject Teeny, a minimal init system that we also customize into the entry point for each container. Containers are created with Teeny as PID1 and configured to pause the application on startup. This gives us time through NRI to wait for all the pod containers to be created, attach to storage, start platform services, and do all the necessary legwork to actually get the workload bootstrapped. Once everything is ready, then we use NRI to send a signal to Teeny through a socket to unpause and hand over to the container's actual entry point. For teardown, when a container stops, we use OCI post-stop hooks to handle all the cleanup sequence. We detach the storage, we stop the platform services as mentioned before, remove the container from CPU isolation, and we clean up resources like volume containers and directories that we all need for all the setup earlier. We do clean up almost exclusively in OCI hooks rather than NRI because OCI hooks are guaranteed to run once they're part of the OCI runtime specification and runc has created a container. In contrast, the NRI plugin has to be up and running to handle events actively. And there's always a potential for missed events if the plugin is not available. This orchestration pattern of using Teeny for coordination, NRI for setup, OCI hooks for teardown is how we compose all these extension points into a complete system for our new runtime stack. Next, I'd like to share some guidelines that we use ourselves for kind of deciding when to use each extension point. So for emission webhooks, as mentioned earlier, we use it for modifying the pod specs before scheduling, for things like injecting platform-wide configuration, enforcing policies, or setting resource quotas that doesn't need runtime decisions. They all run at the API server level before any node is actually involved. In NRI is used for container runtime coordination. We use it whenever we need to modify the container's OCI runtime spec at runtime. We orchestrate container startup sequences. We make decisions based on the actual state of the node. For OCI hooks, we use them for very simple lifecycle event operations, and for things that we actually need to modify the container directly for. They're great for cleanup when containers stop, or any per container operation at lifecycle boundaries. They're stateless, they're event-driven, they're guaranteed to run because they're part of the OCI runtime specification. The key insight here is being able to choose the right extension for a particular use case. Next, I'd like to share some experience of us running these runtime extensions at scale in production. So far, we've successfully migrated to this new architecture at massive scale. We've been able to migrate the vast majority of Titus workloads to a new runtime stack in a pretty short amount of time. And I believe by the end of this week, we'll probably be about 100% on this new stack. There has been 0 major incidents from the migration itself, which is a huge win for such a fundamental infrastructure change. We also now have better observability. We can integrate tracing across all these different components. The separation in all these distinct extension points make it much easier to understand what's happening when things actually go wrong. Maintenance is significantly simplified too. The clear separation of concerns make the code base easier to understand and modify compared to the old monolithic, esoteric runtime layer that we had before. Beyond proving the extension point approach works, the broader migration to stock kubelets and containerd has been great for us. We now have access to alternative snapshotters for faster image pulls, and now we also have the space to innovate and opportunities to contribute back upstream and participate in an open source container ecosystem. We did have some challenges along the way. The first thing here was the NRI plugin availability problem. If a pod actually gets scheduled to a node when NRI is down, they will not actually get any customizations. And since kubelets does not know about NRI, it'll happily just support having that pod running on a node. We solved this by using a node problem detector that watches the NRI systemd service on the node and taints it as unschedulable if it ever goes down. We also tied the lifecycle of kubelets to both NRI, the NRI plugin, and containerd, so kubelet won't start accepting workloads unless everything is ready. The second challenge here is that we ran into an interesting issue with a global lock within the containerd's NRI implementation. Containerd's NRI implementation uses a global lock, which means it can only process one RPC at a single time. This is understandable since it gives a strong guarantee that events will be processed in the order they're received. But at our scale, with thousands of pod events happening when we're quickly bin packing worker nodes, that has caused significant delays. As you can see in this picture here, we show a trace that shows how long it took to do a stop pod sandbox operation. So that span shows 9 seconds. And of those 9 seconds, you can see the NRI lock span takes up a full 7 seconds. And this was during a very busy time on the node when we were scaling 96 pods on a 96 CPU machine with thousands of operations happening at the same time. We worked around this issue with a custom patch that enabled per pod locking instead of a global lock, which allowed us to process different pod events concurrently. We've opened the upstream issue to service this problem and discussed potential solutions with the community. And actually, we recently opened a PR to kind of propose the solution for this as well. So here are some key learnings from our migration journey. First thing we learned was to balance pragmatism with platform purity. Extensions like NRI and OCI hooks let us meet Netflix's unique workload requirements, things like multi-tenancy, thick containers that run systemd, that pure Kubernetes patterns cannot handle, at least without having the need to fork. The key here is migrating existing workloads transparently to first maintain trust with users, which builds the foundation for us to then iteratively move towards the more standard patterns over time. Second, our lift and shift strategy was crucial for reducing risk. By reducing existing code to extension points before rewriting, we could validate the architecture with real production workloads. This gives us confidence that the new data plane worked correctly before we actually decide to make iterative improvements. It has enabled a seamless transition that users did not even notice. Third, observability was absolutely crucial. With such a distributed system spanning scheduler, kubelets, containerd, NRI plugins, OCI hooks, having end-to-end tracing was essential for debugging issues. My colleagues Artem and JP gave a talk earlier called Where's My Pod? That goes very deep into how we built the observability across the stack. If you missed it, I highly recommend watching it after it becomes available online. It's a great companion to this talk. So here are some resources and links. I have some reading material on documentation on NRI implementation, containerd, the OCI runtime spec, and I also share 2 blog posts here. One is for an issue that we ran during the modernization project that's not related to runtime extensions, but actually containerd, how it actually does user namespace support in terms of scaling mounts. If you have an image with many layers, it just causes the kernel fallover. You have just like bin pack 96 pods. And then also the blog post on migrating complex system infrastructure, and it's also linked there. On the right side, I have a sampling of different contributions that resulted from this modernization effort that we made to upstream. We have many NRI PRs open and actually merged, and we also have some containerd ones. That has been great, showing how we've been able to kind of coordinate and collaborate with upstream maintainers to solve some of our issues. Next, I'd like to give a shout out to all the containerd and NRI maintainers, Christian, Antonio Oeja, Sam Karp, Mike Brown, and many others for their guidance in helping Titus start embracing the cloud-native ecosystem. And with that, that concludes my talk. Thank you for staying through. And here are some QR codes. So on top one, please give me feedback if you have feedback. And the bottom here, we're hiring. If you think this talk was interesting, please take a look at all the job listings. Thank you. All right. And I'll open the floor for questions. I guess, oh, sure. Oh, go ahead. Sorry, can you speak louder? Sorry. Okay. Yeah, I think it's as long as it's expressed. Oh, sorry. The question was, sorry, what was the thing that you're trying to add? Okay, CI devices. Okay. Okay. So the question was, is there a way for me to kind of add CDI devices to the POSPEC or to the container through these mechanisms? So I guess since I'm not really familiar with that is, but as long as there are ways to kind of express that in the OCI runtime spec, then you can use NRI to kind of plug those in. Or if it's actually a device, then there might be things you can do to kind of directly kind of share those devices with a container at the OCI runtime hook level or NRI. It also all depends on the lifecycle hook that you can actually use. For example, if you need a container to be created, you can use NRI to kind of interact with it. OCI if you need to. Yeah. Okay. And let's see. This gentleman over here, I'm not sure. I guess I'll walk over. All right. Yeah. Sure.
In the recent version, I do see that you have an example with systemd, right? You guys need writable C group, right?
Oh yeah.
You also have the same issue with Meta, and I think in the recent version of containerd, like containerd 2.0,
right.
something like that, and the newer version of runC, you can also configure the runC to have.
Oh yeah.
C group,
Yeah.
Doing some extra hacks. We also struggle with that.
Yeah. Oh, thank you for sharing that. Yeah. That's all part of the modernization effort, just so we can actually leverage solutions like that. So thank you for sharing that. Rather than a question, it was a gentleman actually sharing a great solution for kind of being able to modify C group FS through runC interfaces in the newest release versions. Over here.
Hi. Thank you for the presentation first. I'm wondering if there is anything on any of these available open source or somewhere for me to replicate? Because
yeah.
I'm more or less in the same situation of getting out of EC2 into Kubernetes.
Yeah, so right now, all of this code is mostly, I got you, zero, I'm out of time, but I can just stand on the side here if you like, and then we can talk about it. Thank you very much again. Thank you.